beginning of my graduate studies, I attended a lecture by Nico Kinzel from Atelier 10, who started his lecture by saying that a well-designed building, meaning a well-designed shelter, is able to accommodate many of the functions that we want to achieve in any given climate through its architecture. The more we are able to let the architecture do the work, the smaller our systems will be. A high-performance design is primarily centered around facade optimization, daylighting, shading, systems optimization, water and resource conservation, in addition to thermal and visual comfort. The basic question that needs to be answered is what needs to be achieved in order to provide shelter. The basic aim is to move away from a conventional design, and there is a relatively clear procedure in how we can achieve a carbon-positive development. Beginning with a conventional design that can achieve the building's pragmatic requirements, several questions are brought up. What is the climate? What degree of shelter is needed? And what part of this shelter can be achieved through the building envelope? How much energy is needed in order to effectively condition this shelter, and where does this energy come from? And finally, what can be done in order to mitigate these energy requirements in terms of environmental sustainability? Many people start the investigation from different standpoints, beginning with the notion that a green building needs to have significant renewable systems in order to perform or be effective, overlooking the architectural design that can be meaningful and lead to a really energy efficient building. In order to optimize the design, there should be an integrated process and looking at the interrelated elements. Looking at the buildings that have been constructed during the last 30 or 50 years, the process that was followed was typical. The architects were designing the buildings, and the engineers were putting the HVAC systems. And that led to energy systems optimized by engineers and energy loads optimized by architects. When what we need should be an integrated design process that would lead to an architectural system optimized by a design team. Looking at the various design phases of a building, of a design, the majority of decisions should be made at the very early design stages in order to achieve significant money and energy savings. The initial sketches that determine the massing of the building, the attitude to the building enclosure, and the pragmatic energy distribution are setting the stage for all the energy to be used later. It is therefore evident that the building envelope can have a significant impact in the reduction of the building's energy demand while improving its life cycle environmental impact. And one way to achieve this reduction is if we implement thermal energy storage in the building envelope. Thermal energy storage can be applied either as sensible energy storage, where heat is transferred to the storage medium leads to temperature increase and there is low heat storage potential, or through latent energy storage with PCM, where the heat absorption or release happens when the material undergoes a phase change. When we use phase change materials, there is a high energy storage density and heat is stored at a constant temperature. This way, when latent energy storage with phase change materials is implemented in the building envelope, it is possible to have smaller mechanical systems and systems that would achieve better efficiency because the space cooling shifts from daytime to nighttime. It is possible to use the solar energy for heating because of larger accumulations capacities in the materials. We can achieve better temperature control because there are lower temperature swings within the space, while it is possible to have high thermal mass in small material volume in lightweight buildings. In order to evaluate the performance of phase change materials, an integrated analysis is needed, and sometimes it constitutes of multiple interrelated variables. This is why we need multi-objective optimization. In this case, sometimes there are multiple, usually conflicting objectives that need to be optimized, a specified number of constraints that need to be satisfied, and the number of design variables which, when they change, affect the objectives that will be optimized. When we run a multi-objective optimization tool, the results that we get are usually a set of alternative solutions involving different trade-offs named Pareto optimal or non-dominated solutions. Multi-objective optimization consists of three phases: model building, optimization process, and the decision-making process. The decision-making process is basically because of the different trade-offs. We need to select which trade-offs, which alternatives are closer to the result that our specific design has, our specific project has. The methodological approach of my PhD starts with a general analysis of the Greek and the European building stock, which leads to a classification of non-residential buildings according to their use, size, and metabolism rates, based on the boundary conditions of this study, which are climatic conditions, usage, legislation, and architectural boundaries. The optimization problem is formulated, which means objectives, constraints, and design variables are selected. This leads to the building of the model building. After the building is created, it's validated by comparing the simulation results either with small parts of experimental measured data or with another whole building simulation of a building that is studied in Cyprus with a different simulation tool. The optimization methodology is implemented in the case of Greece. 4 different cities are selected, 1 for each climate zone in Greece. And after the results are produced, there is a decision-making process in order to articulate the results in a country scale, and then a GIS analysis to extrapolate the results in a format of a map in the country scale. After the optimization methodology is implemented in a country scale, it is then implemented in the European scale. 1 city of each climate type is selected, and then the decision-making process also follows to articulate the results on an EU scale, and then move to the GIS analysis for the extrapolation of the results again on the EU scale. The final results refer to proposing the optimal alternatives for each climate type. The boundary conditions that were mentioned before refer to climatic conditions. The Köppen classification system is used for Europe, so there are 10 different climate types and 1 city is selected for each climate type. The usage that is selected is office buildings because they are one of the highest contributors to energy demand. Regarding the technical and legal requirements, the Energy Performance Building Directive of the EU is followed, and specifically the requirements for the nearly zero energy buildings. And for the needs of this study, 1 completely office space and 1 completely closed office space is used in order to see what is the difference in performance between the 2 spaces. These are the most typical used office spaces. The optimization problem is solved in the Design Builder Simulation software, which is a 3D modeler which includes 9 different tools that are connected. One of them is the multi-objective optimization tool, which uses a genetic algorithm, and specifically a non-dominated sorting genetic algorithm, NSGA2 method. The Design Builder Optimization tool has a few limitations, with most important that it can reach an optimization of only 2 objectives, while including up to 10 design variables in the analysis. For our methodology, the objectives to be optimized is to minimize the total carbon emissions while minimizing the cost, constructional and operational, while keeping the discomfort hours under a certain level. The variables that are examined start with building orientation. We use orientations for every 45-degree angle. Window-to-wall ratio starting from 20% to 80% with 10% increment. Shading percentage of the facade, again starting from 20% to 80% with 10% increment. Construction templates are created with various insulation materials and thicknesses, different thermal mass materials that can be either conventional materials to achieve sensible storage or phase change materials that in order to achieve latent storage, and various positions, relative positions between the thermal insulation and the thermal mass. And also 2 control strategies are applied in order to control or try to control the melting and solidification cycle of the PCM on a daily basis. This tool can be used in the early design process, and the basic aim is to answer one question. Is it possible to distribute phase change materials in the building envelope in a way that we can control charging and discharging on a daily basis, even in air-conditioned buildings, and achieve an improvement in the building performance? And if so, what are the optimal combination of parameters leading to this achievement in different climatic conditions? Thank you very much.